So, so first of all, I'm going to give a very brief introduction about seismic noise interferometry, that during this workshop we already know everything, so it's going to be super simplistic. But so as we know, seismic noise, it can be defined as the continuous signal that we record in all the seismic stations on Earth, that it can be recorded and observed in absence of large amplitude signals, and can be earthquakes, tremors, glitches, and all these signals that we have seen in the past days. So here I showed you a typical power spectral density of the seismic noise, and we know that we can define different frequency bands that are associated with different mechanisms. And as we have learned also in the past days, these two peaks of energy are associated to different ocean wave interactions. So if we have two stations located somewhere, how can we study the subsurface with noise? So also, as we have seen, just correlating the two seismic noise recording, we can have an estimation or an approximation of the Green's function of the medium. This Green's function in mathematics is very useful because we can solve very easily, not for everybody, not for me, but very easy differential equations, ordinary differential equations. And in physics, in seismology, we can understand this Green function as the seismic response of the medium to impulse responses. So we have here positive and negative lag times because we have the seismic sources located somewhere in the surface, and then this scenario is analogous mathematically as the one of the seismic station acts as a source, and then the waves traveling from one station to the other one and to the other way around. And that's why we have two different signs in the time. So here I showed you a typical correlation, and also we have seen we can retrieve body waves, surface waves, and coda waves just correlating seismic noise recordings. So this is the so-called seismic noise interferometry approach, and is mainly used for imaging and monitoring purposes. So here I would like to show you some alternatives to process the data that I think part of the audience is very well aware of these techniques, but maybe for others it can be very interesting. And I would like to show you the philosophy and the applications that we can do. So this is the typical workflow that we do. We go to the field, and then we deploy seismic stations. Then we wait a little bit of time. Then we take the data. We go to the field again and retrieve the data. We get the data in real time. And then we do different pre-processing steps that I think sometimes is a bit personal. So it changes from every group of every person. But normally we check the data, the quality, we study the frequency content of the signal, we remove the instrument response, we check if there are gaps or many other techniques that we can do. Then we correlate the seismic noise recordings that we have. Then we stack. For imaging purposes, normally we just stack all the data that we have. And then for monitoring at delta t, we stack during 3 days our data, 5 days, 1 week, or depending on the goals of our study and the quality of the data. So this is the normal correlation, the classical correlation that we apply. Here is just a geometric normalization, but you can normalize as usual, just 1 divided by 2, and that's it. So, and this is the classical approach, and it works very fine, but also we know that sometimes if we have a lot of earthquakes in our recordings, we need to normalize and to do some normalization in time or in frequency in order to avoid the effect of these large amplitude signals in our noise, in our recordings of the correlations. So here I showed you an alternative approach, that is the phase cross correlation, and here you have the equation that, as you can see in the equation, the amplitude of the signal, it doesn't appear. It's just the exponential of something. I am going to show you a little bit how this phase cross correlation, where it comes from, this correlation. So here I show you, so in signal processing, it's very common to compute the analytical signal, and this analytical signal is computed as the real time is just our seismogram, and the imaginary part is the Hilbert transport of this, this is a mistake, of the seismogram. So we have the real part, our seismogram, our signal, and in the imaginary part, the Hilbert transform. And then now we have complex numbers, and with complex numbers, we can redefine this and to represent this as the amplitude and the exponential. This amplitude is the instantaneous amplitude, and this one is the instantaneous phase. So this phase is not related to the phase of the Fourier transform, it's the instantaneous phase. And here you have a representation of one signal, one point, at one specific point in the complex domain, we have the amplitude, the module of the vector, and the instantaneous phase. So in this way, we can build this equation, and then if we have, for example, if we correlate two different points, two different signals, it's just a summation of vectors in this complex space. And here I would like to show you a comparison between three different methods. So the phase cross correlation, the classical correlation without any pre-processing techniques, and then the close correlation applying the one-bit normalization. That is the most common approach. So here we have our reference trace that normally is the stack of all our data. And then here I represent, in a very simple way, our data set. So we can select randomly 5 hours, for instance, of data. We cut the signals, for instance, every hour, depends on the goals of the study. And then we select 5 hours randomly. And then we compute the correlation with our reference. And then we obtain a dot here in this plot. In blue, the PCC, in red, the classical correlation without preprocessing, and in green, with the preprocessing. Now we select other random 5 traces, and then we compute this again. And we can repeat this process in an iterative way and for different stacking lengths. And at the end, we can get some plot like this. So in most of the cases, we can see that the phase cross correlation has a very rapid convergence, and we can retrieve correlations very stable with less data, much less data. But, and here you have the comparison. But as Martin Simmel always says, there is no a best method. It depends on the goal of the study, it depends on the quality of our data, and it depends on many things. Yep. Thank you, yes, I skipped it. It's just the correlation at 0 lag time between the reference and the correlated trace that you take, the stack of these 5 hours or 10 hours. Yeah. So just how similar is this stack to the reference. And then at some point, you are just, it tends to want to be similar. So, yeah. And then with the same philosophy, we can, yes. Here I show you just an example, one application of the PCC, and then of one study published a few years ago, and we can identify very clear all the different phases. And here we don't care about earthquakes, because this method, it doesn't depend on the amplitude. So we don't need to pre-process the data more, we don't need to remove the earthquakes, we don't need to do anything, and we can retrieve very nicely all the different phases. With the same philosophy, we can go to the stack, and there are many different approaches with many different filters. One is the linear stack, that is the classical approach, that is just an average of our correlations, and then we have others, the phase stack, time frequency phase weighted stack, and many phase themes stacks. So we can define, for instance, just quickly the phase stack. We have the linear stack, that is just the average, and then we can use this summation of the exponential, that is a measure of the coherency, as a weight. And then if the phases are coherent, then we can have a big weight, and then the stack is going to have this peak. But if the signals are incoherent, then we are going to mitigate, in this way, these incoherent arrivals. So it's a way to enhance the signal-to-noise ratio. We have in the expression here a power, and this way with power we can control how much we want to filter the incoherent noise. And then we can define, well, here is just the S transform, because we can define another stack that I am not going to go into details, but I want to show the S transform that discussing with some people, and some people are aware of it, but others not, and I think it can be very useful. So the S transform is just the Fourier transform, but here we add a Gaussian function, and this Gaussian function depends on the frequency. So this is as a Fourier transform, but we can gauge much more resolution at certain frequencies, because with the Fourier transform we use a fixed length in the window, and then with this one we have like the window of to apply the Fourier transform is variable. So So here I show you just the S transform of one seismogram, and here you have the different Gaussian functions, and then we can see that we gain a lot of resolution. And here I would like to show you an application. So this transfer has been used in many approaches. For instance, here to develop this phase-weighted stack in the time frequency domain, but also we can use that when we study our velocity changes, when we do monitoring, because sometimes we have, yes, here is just because we have all the codes are available and open source and you can download and play with them. It's very easy. So advertisement. So yes, so here is one study that we published a few years ago that I am not going to explain much, but we monitor one power plant, and then we have a very complex pattern of many changes in the similarity or also in the velocity changes, and then you can apply this transform to do a time frequency representation of the changes. And then it's a beautiful way because you can, for instance, if you are looking for rapid changes in your time series, you can say, okay, one changes that happens every day or every week, or also here we have the seasonal changes. So it's a beautiful way to quantify the seasonal effects, and you don't need to correct if you have different tendencies of different changes. So then once we have correlated our data, we stack, and then with this similarity approach, we can see how many days of data we need to stack, depending on the goals of our study. Then in the rest of the talk, I am going to talk about monitoring, and as you know, we can monitor changes in the mechanical or scattering properties in the medium. So here is a very simple diagram of how the waves travel, depends on the lag time you are in a multiple scattering regime or not. So yeah, it's just a simple representation. So we have a mechanical change that it can be that we have less fluids in the medium, the waves are going to be delayed or are going to travel faster. So we are going to observe this delay. But we have a structural change that it can be maybe a magma chamber that collapses, and we have the scatterers are located in different positions. The waveforms are going to be a bit different. So are the changes that normally we can monitor with these techniques. So here I am going, we don't have much time, so I am going to talk just about the similarity. It's very easy to apply. We don't need to do any assumption, and it has a great potential. So here we define the similarity as just the PCC of the reference and the correlation that we are interested. In this case, for the study that I am going to show you, we compute this at all the lag times and the sliding window along the coda are for all the days. So we are going to retrieve a correlation matrix, similarity matrix that we can study. So I have 10 minutes. Perfect. So now let's travel to Canary Island. Canary Island is located here. This is Africa, this is Spain, this is Italy. We are located somewhere here. And in 2011, there was a volcanic eruption. Because now, yeah, so we want to see with these approaches the potential that, or maybe the high resolution that we can get in complex environments. So here, this is one of the smallest, it's the smallest island in this group of volcanic islands, and it's called El Hierro. And in 2011, this National Geographic Institute started to record a seismic cluster here in the north. Very intense, very, very intense. And then the institute deployed several stations here in the north in order to record this seismicity. But as you can see in the plot, the seismicity was migrating southward, and then we don't have any station. And at the end, the eruption was located here. It was a submarine eruption, super small. So we don't have stations around this volcano as usual, as we have normally in monitoring studies for volcanic eruptions. So here I showed you the data availability that we have. This is 2011, this is 2012, and with red line I represent the eruption. So as you can see, we barely have data before the eruption. We have this station that we have a lot of data. No, this one that is located here, but the government decided to open a wind park close to the station, and then we cannot use it. So we only have just like 7 stations with barely data. So that is the challenge. We are going to apply these techniques. We are going to apply seismic noise interferometry in a very small volcano with a very tiny eruption that happened here. The spatial distribution of the stations is terrible, as you can see. It's not around the volcano. We have very scarce data, and also, if it's not already a bit complicated, we had a very strong volcanic tremor in a very wide frequency range that contaminates our data. Here I showed you the spectrogram, 2 windows, just at the beginning of the eruption and at the end of the eruption, and we can see that the eruption started one specific day, abruptly in October. very abruptly. So one specific day was explosive eruption and started. And we can see that there were several earthquakes, many earthquakes before, actually around 11,000 earthquakes in a few months. And here you have the spectrum of the end of the volcanic eruption. That was a bit chaotic. There was several pulses in the energy with several different activity, and was a bit complicated to determine the end of the volcanic eruption. And here I show you this similarity matrix that we compute for an autocorrelation. So here we take this station that is located here in the center, and here is with the colors I represent the similarity, and here you have the lag time, and here you have the time. And this black line represented surface deformation, measured with a GPS station that is located over there. So here we can see many different things, and it's just very easy. The computational cost is nothing. And then we can see here we detect the eruption, very clear. The first result that we obtain is here we can see the end of the eruption, super clear, was a seismic. So here we didn't see this sudden drop in the energy and so on. So we interpret this change as the end of the main magmatic activity. And also we could see some things, some drops in the similarity that coincide with magmatic intrusions that happened before the eruption. And here I show you a comparison with a cross-correlation, because discussing with all of you, I always say I like much more autocorrelation, but it was difficult to explain without a plot. So here I show you an example. This is the autocorrelation, and here is a cross-correlation of two stations very close. And here I see that we can see more or less the same pattern. We can see the eruption, we can see some changes before, we can see the end of the eruption very clear, we can see the magmatic intrusions, but the pattern is more damp. Why this is this? Well, my hypothesis, here we have the sensitivity kernel, so with autocorrelation we are very sensitive to the changes or the things that are happening just beneath the station. But with cross-correlation we take into account a wide space. So if we have a magmatic intrusion in the middle of our array, maybe the pattern, the stress pattern is easy, and then we can observe the same in all the areas. But for instance, there is a study in Iceland, very nice, that they have a magmatic intrusion with a certain inclination, and then you have the Coulomb stress pattern in the surface is very complex. So if you study these changes in one area that is in a compressive area, then the velocity should increase, but if you are in a station, it's going to decrease. So if you do the cross-correlation between different patterns, then the waves are going to change the velocity during the wave, and then you are going to observe an average of these changes. So sometimes depends on the pattern of the geometry of the changes or on your area of study, is worth it sometimes to compare, or maybe to take correlations, cross-correlation that are in the compressive area and the extension area and compare different things in order to not mix everything, because the interpretation, it can be a nightmare. And yeah, so here we see that there are some changes before the eruption, but was a bit tricky, no? Because this is a precursor, it's not a precursor, what is this, no? And then here we focus, here I show you the results. So in this lag time window that we saw some changes, I just average in this lag time the similarity, and then I represent here the result for the different autocorrelations before the eruption. So the Spanish Geographic Institute, National Institute, they distinguish between different pre-eruptive phases. They use all different instruments, all the stations, GPS, thermometers, gas monitoring, submarine cameras in order to monitor very well this eruption, because we don't have many eruptions in Spain, and then everybody was very excited. And then we wanted to see if this change that we observe here is significant, means something or not. So in this case, I got crazy because I wanted to know if this change is significant, or if I say that it's a precursor, because I want to find a precursor before the eruption. So we can be very biased sometimes with our results. So I wanted to apply some statistical approach in order to in order to distinguish if that change is significant or not. So in many fields, this is very well known, the change point analysis, and then it's just a statistical approach to find points of change. Change of what? It can be a change in the mean, it can be change in the root mean square, it can be change in the trend, it can be change on any statistic that you are interested. you can find in Python, in MATLAB, is already implemented and it's very easy to run. And then we obtained different segments, different periods that were statistically different between each other, and they fit very, very well with the phases, periodic phases that the National Geographic Institute got. In some stations, here we have one gap, so it's complicated to detect things. In other stations, we don't have much data, but for instance, in this one, only with one autocorrelation, one station, vertical component, we could detect in an automatic way all the periodic phases. So sometimes we don't need just to focus on the precursor, we can see many different things. And in this case, only with the similarity, with the phase cross correlation. And that's it, just to finish. So we also located the changes, this precursor, this is a tomography study, because all the seismicity, as I said before, started in the north. So the magma chamber is expected here in the north, and then immigrated with different complicated patterns until the eruption was here. And we found some changes before also the intrusions that we can see. Here I represent in the first panel the seismicity, and here we didn't have seismicity, so we were not able to see with the spectrum. So this was like, the interesting. So and here you just compare all the changes for the different lag times during the entire period of our data. And that's it. And just to conclude, so just to remember that we can use this similarity approach to determine the resolution, the time resolution that we can have. And before running everything, we can say, okay, I have resolution of 3 days, of 2 days, of 1 day, and you can already quantify the sensitivity of your approaches that you are doing. The S-transform, that it can be also useful to decompose in the time frequency domain our data's analysis. This comparison with the autocorrelation and cross-correlation, and this change point analysis that is very easy, and it can have a lot of potential. And that's it. Thank you.